What's up? This is Professor David J. De Los Reyes. We are on photo finish on integral calculus. The topic this afternoon will be a board exam problem. Okay, let's proceed. I am now on lesson number 83 on my channel under the topic integral calculus, subtopic volume, miscellaneous volume. The topic for this afternoon will be a board exam problem. Okay, I will try to read the problem. This is a board exam problem, guys. Once upon a time, this came out in the board exam for engineering board exams, specifically electrical engineering. Okay. A cylindrical vessel, 5 inches in radius and 20 inches high, is full of water. It is full of water. We got a cylindrical vessel. The radius is 5 inches and the altitude is 20 inches. It is slowly tilted until half of the base diameter is exposed and then restored to its original position. Meaning, if this is a pool of water, the cylindrical vessel is tilted until such a time that half of the base diameter is exposed, meaning the water spout already or came out from the cylinder until such a time that the diameter of the vase is exposed. Meaning the top portion of the half portion of the diameter has got no more water and the bottom top half portion is with water. So we stop. Okay? So some of the content of the water is actually came out from the cylinder. Okay? Then it was again tilted or erected upright. The question is, find the volume of the water remaining. Okay, after some water was or came out from the cylinder and it was erected again upright, the question is, find the volume of the water remaining and the depth of the water. So supposed to be, we removed some contents because we tilted it, then we erected it again upright, and the question is, how high is the water remaining and what will be the volume? That's a board exam problem, guys. So the configuration is something like this. We got a cylinder here, the height is 20 inches, the radius is 5 inches. We tilted it, okay, until half of the base diameter is exposed. Half of the base diameter is exposed. Okay, so the portion of the cylinder with water still is the half bottom portion until half of the diameter is exposed. So meaning the top portion is without any more water. Okay, then it was erected again upright. Okay, so obviously, if it was erected upright again, okay, this should be the remaining volume. Okay, and the problem is asking how much is the volume and what will be the height. That's a board exam problem, guys. I think this is where, I don't know, maybe 15% or 20%. Because this is one of the problems under mathematics. Okay? And actually under mathematics, under electrical engineering, there are 10 problems. And this is just one of the problems. So one topic of the board exam is actually integral calculus, computation of volumes under miscellaneous volume. This is a board exam problem. So if you do not know integral calculus, you do not know how to set up the differential volume, you're gone. Okay, let's proceed with the solution. Okay, we try to draw the cylinder on the XYZ plane, X, Y, and Z. For the meantime, I interchange Z and X because originally this is Y, right? And this is Z. But for the solution, actually you can interchange the notation, okay? So I will make this as the Z-axis, this is the X-axis, and this is the Y-axis. So if we try to graph the cylinder when it is erected already upright, the configuration is something like this. Okay. The shaded portion is this one, the one in red. Okay. So actually, if we try to draw a vertical line, and this is a horizontal line with respect to X, you actually created a right triangle. Okay. It's a variable right triangle. Coming from this point here, it will be 0, but as it goes from this point here to this, it's growing bigger until it reaches the middle portion. Then from the middle portion to this point here, it again vanishes. As it reaches this point here, the variable right triangle is again 0. So actually, we are given a variable right triangle. Okay, let's proceed with the solution. If this is the x-axis and this is the y-axis, this is a circle, right? So if we try to take the equation, it will be an x squared plus y squared equal to 25. 25, it is 5 squared, the radius of the circle. And what's this? What's this? Hold on, I'll get my straight edge. At this edge of the cylinder, if we try to erect a vertical line, okay, this total length is actually 20 inches. And the value of x is 5. So this point here is with coordinates 5 and 20. For this one, it will be 5 and 0. Considering the x and z axis, okay? We need these points here. Because when we try to look for the relation of the variables, we need this height. Okay, let's proceed. I will try to bring out this variable right triangle. It is this. This length here is x. Why x? It is along the x-axis. Okay? And it is at the floor section. It will just be simply x. And what is this length? It is z. It is along the z-axis, right? So this is a. So meaning the variable right triangle is actually with the base x and z. Because as this variable right triangle moves from this point here, going to the middle, then going to the middle to the other side, okay, it varies. So x is variable, z is variable. Then we try to project this one here. Okay, we will create two right triangles. This one is actually the first right triangle over here. This is z, and this is x. The bigger one, from the origin to this, that is actually with the length 5 inches. Okay, and the vertical line is actually with the height 20 minus 0, that will be 20. So this is 20, this is 5 inches, this is z, this is x. So that is where we will get the relation of the variables. Okay, let's try to take the value of tangent of theta. Tangent of theta will be this side here, over this, z over x, equal to 20 over 5. If we try to compute for z in terms of x, z is for x. Z is variable, x is variable, equation number 1. Okay? Then from the equation of the circle, this one, we need this relation here. From the equation x squared plus y squared equal to 25, 25 will be 5 squared. We will solve for x. X will be, we transpose this one, then we'll take the square root. So x will be the square root of 25 minus y squared, the square root. Equation number 2. I am just deriving the relation of the variables for the meantime. Okay, let's proceed with the volume. If we try to compute for the volume of the differential strip, the volume is actually the area of the triangle times its thickness. So differential volume is actually 1/2. I am now formulating the differential volume, 1/2 of base times height for any triangle, right? Luckily for this problem here, it is a right triangle. Because the base is actually horizontal and this is vertical, and it moves from 5 to -5. Okay, it varies. So if we try to substitute now, this should be 1/2. What is the base of the variable area? It is x, right? So this is 1/2 of x, okay? And what is the height? It is z. It is z. And what is the thickness? Because this is just an area, to get the volume, there should be a thickness. The thickness is just dy. Why dy? Dy because the thickness moves along the y-axis, right? Right? It moves from 5 to -5. Okay? Under the xyz plane, this goes positive and the other side goes negative. So this is 5 and this is -5. The thickness moves from 5 to -y along the y-axis, so our thickness is dy. Okay? So substituting now, this should be 1/2. What is x? The square root of 25 minus y squared. Okay? Times, what is z? Z is 4x, right? 4. And what is x? 4x. So this should be 4, the square root of 25 minus y squared. Right? So what will come out? 4 over 2 will be 2. The square root. Okay guys, I will try to erase that one. I want to show you that one. I expedite the solution, guys. So differential volume will be equal to, it is 1/2. This is square root, this is square root, so this is 25 minus y squared raised to the 1/2. Raise that again to the second power because it is twice, right? What will come out? Times 4. So these two here cancel with this, and differential volume will be 4 over 2 will be 2 times 25 minus y squared. This is times dy. Times dy. So actually we are now given differential volume as a function of y, dy. And this is now integrable. Okay? So differential volume is actually 2 times the quantity 25 minus y squared times dy. The simplification of this square root times this square root is this. So differential volume is 2 times the quantity 25 minus y squared times dy. Integrating both sides. The integral of differential volume equal to 2 is constant. 2, the integral from -pi to pi of the quantity 25 minus y squared times dy. Why -5 and 5? You can see it. The thickness dy moves along the y-axis and it will come from 5 and -5 to cover up the total volume, right? So this is -pi to 5. Luckily, the integration is easy money. This should be 25 times the integral of dy, it is y. Y squared, it will be power formula, it is y cubed over 3 from -5 to 5. Substituting the upper limit, it is this. Minus again, 2 times the value of the lower limit, which is -5. If we try to simplify this one, the upper limit will be 500 over 3. And the lower limit, the overall sign of this, it will be negative. And this is preceded by negative sign, so this is plus. Okay? It is 500 over 3. 500 plus 500 is 1,000. Common denominator 3. The remaining volume will be 1,000 over 3 cubic inches. And this is actually approximately 333.33 cubic inches. Okay? That's the volume of the one remaining inside. And from the equation, volume is equal to pi r squared for a right circular cylinder, we now know the volume of what remains inside, so we will substitute it. 1000 over 3 equal to pi. The radius of the cylinder is 5. 5 square is 25 times the unknown height. Okay? Then try to multiply all the terms by 1 over 25 pi. 25 pi. So the right hand side times 1 over 25, this 25 pi cancels. So height now will be 1000 over 3 times 1 over 25 pi. And if you use your calculator, the resulting height will be 4.24 inches. Meaning, if this is the right circular cylinder, and originally this is 20 inches, 4.24 is approximately 5, so this is 5, 4. It is something like this. This is the remaining volume. 4.24 inches, and the volume is 1000 over 3 cubic inches. Oh, that's it, guys. That's a board exam problem. So this is now an application of integral calculus under volumes, miscellaneous volumes. So if you are on the board exam, you are on your own. So it's up to you to recall your knowledge of mathematics. This is one of the problems under electrical engineering mathematics problem. It is hard. Okay? So if you are not prepared, you're gone. Okay, good afternoon, Los Angeles.